Hey guys, Miss Lowry here. We're going to be talking about mirrors, mirror properties, and mirror ray diagrams today. And we're going to talk about two main types of curved mirrors, concave and convex. And so a convex, also known as a diverging mirror, looks like this. And as light rays come in, no matter what the shape of the mirror is, it's going to obey the law of reflection, meaning that if you draw a normal, a line that's perpendicular to the surface, the angle at which the ray comes in is going to be the angle at which it leaves. So it doesn't matter if the ray comes in down here. I should curve that a little more. The angle at which it comes in is going to be the angle at which it leaves. So if you trace back to where these rays converge, they're going to converge on a point that is quote-unquote behind the mirror. So if your object is over here, they're going to converge on this point. And that's the virtual side. This is the real side of a mirror. It's the opposite that of a lens. Okay, and we'll talk more about that in just a second. And just remember that convex or diverging mirrors have negative focal lengths. Okay, so like, negative 2 centimeters or whatever. An interesting thing to note, if you've ever wondered where the center of curvature, where that comes in, we talked about it a little bit in the last lesson. Your center of curvature is always equal to 2 times your focal length. So your focal length is your center of curvature divided by 2. If you took your mirror, your curve, and made a sphere out of it, we always deal with spherical mirrors in this class. If you put the center of that sphere, that would be your center of curvature. Okay, and then half of that is your focal length. Okay, the second type is a concave, also known as a converging mirror. Okay, concave or converging, and it's caved in. Okay, if your object is over here, the light rays from infinity, once again, they obey the law of obey the law of reflection. So the angle at which they come in equal the angle at which they leave. So they're going to focus on a single point that is on the same side as your object. And concave mirrors always have positive focal lengths. Okay. And once again, you could make a circle, a sphere, a circle out of this mirror and see that the center of curvature is 2 times the focal length. Okay, 2 times the focal length. All right, let's look at some properties of mirrors. The real side, this is the opposite that of lenses. The real side is always going to be on the same side as your object. The virtual side is always going to be opposite your object. Okay, so like on the opposite side. All right, so remember, real means that it can be, the image that's created by that object can be projected onto a sheet of paper. Okay, and hopefully in the mirror lab that you do either tomorrow or the next day, hopefully the mirror lab, you'll be able to actually see a real image being projected, so you can see the difference between real and virtual. You cannot see the image in the mirror when it's real. Okay, when it's virtual, that means that it is quote-unquote in the mirror. This is the ones that we deal with most often. So here's you in front of a mirror. Here's, this is you, this is your image. Your image is quote in the mirror. Okay, it cannot be projected onto a sheet of paper. All right, a couple things. Object distances is from the object, and here too it reiterates the real side and virtual side. For converging mirrors, the distance to the object, remember, is S sub O, and that's from the object to the mirror. It's always a positive value. Okay, if your image is on the real side, so here's our image distance here, our image distance, it's going to have a positive value. So anytime your image is real, okay, that means it's going to be on the same side as your object, and it means it's going to have a positive value, just like the focal length is positive for this type of mirror. Okay. All right. If your image is located on the virtual side, okay, then it's going to have a negative value. Okay, the image distance will be negative. So let's pretend like my image was here. Okay, then it would have say negative 2 centimeters. Okay, it would have a negative value. Okay, objects that are below the principal axis always have a negative height. objects above the principal axis always have a positive height. Okay? All right. For diverging mirrors, the focal length is always negative. And it's always on this side of the mirror. Always, always, always. Okay? Your image will always have the same properties, and we'll talk about that in just a second. But it's always going to be virtual, always going to have a negative distance to it. Okay? All right, let's look at, pull out your ray diagrams for me, please. All right, let's see if I can focus this. Oh, that's pretty good. All right, there's two main principal rays that you're going to use a lot, okay? And there's a third principal ray that you'll have to use. Really, you could use, there's multiple, guys, there's like 5, 6, 7 different principal rays, basically rays that tell you where the image is going to be located. I like to just focus on 2, because that's how many you need to form an image, so that you don't get confused. For mirrors, we kind of need to throw in a third one, when we talk about converging mirrors when the object's at the focal point, because it makes it easier to draw. So the first 2 rays that we're going to use a lot, okay, like almost all the time, these are the principal rays. Principal rays. And they are parallel to focus and focus to parallel. Okay, parallel to focus and focus to parallel. Those are the 2 that you're going to use most often. Mirrors. The third type of ray is called center of curvature. And I'll show you that when we get to that point. Okay. So do you remember SIR, LUR, LUV, and SUV? The abbreviations that I told you to remember for lenses? You're going to have the same exact abbreviations for converging and diverging mirrors. So for a diverging lens and a converging mirror are pretty much have the same image properties. So what that means is if I have an object that is beyond the center of curvature, I'm going to draw a ray that runs parallel. And the second I hit my mirror, I go through the focus, parallel to focus. Whoops. And my second ray is going to be focus to parallel. So you're going to go through the focal point first, and then when you hit that mirror, you go parallel to the principal axis. Remember, you're going to draw the image where the points converge, where those 2 lines come together. Okay? So anytime you have an image, anytime that happens below the principal axis, you can see that you're going to have an inverted image, and so it'll have a negative height value. Okay? So this image is going to be smaller, inverted, and real. Remember, this is the real side for mirrors. This is the virtual side. Smaller, inverted, and real. Okay. For the second, here we have at the center of curvature. So we've got parallel to focus. Get the focal point in there. And focused to parallel. So you go through the parallel or the focus first, and then you go parallel to that. These, I didn't draw these quite parallel. These should line up. This should line up over here, and it should be directly under it. So I didn't draw that completely parallel, and that didn't go through the focal point. Anyway, this convergent point should be a little over. Okay, so basically it's same size whenever the object is at the center of curvature, same size, inverted, and real. Okay, if you want to remember SSIR, you can. Not important, really. All right. Between the center of curvature, when your object is between the center of curvature and the focal point, Once again, same thing, guys. Parallel to focus. Focus through the focal point. To parallel. Okay, so this image here, anytime the object is between the center of curvature and the focal point, this object here is going to be LUR. Remember Sir Lur Love? LUR. Larger, inverted, and real. Sir Lur Love. Okay, Sir Lur. Alright, larger, inverted, and real. Okay. This is the one that's a teeny weeny bit tricky. It's not too bad. Okay. You're going to do the same parallel to focus. So, parallel to focus. If I can get this to work right. Okay, obviously we can't do a focus to parallel, okay, because it goes through, it's at the focal point, okay, so we're just going to go through the center of curvature, so it's going to look like this. Alright, these are supposed to be parallel to one another. At the focal point, no image forms, just like with the lens. Okay, because those lines do not converge or diverge on either side. Okay, so no image forms when your object is at the focal point. And when your object, once again, we can go back to parallel to focus. Okay. And we can also do focus to parallel. So what we'll do is we're going to go from the mirror here, from the object through the focal point. Okay, so that's focus to parallel. And it's going to go parallel on this side. So it's going to go focus to parallel. Okay, focus to parallel. And then our parallel to focus, we're going to, once again, we're going to trace that out to this side, just like that. And our image forms on this side. So Sir Lur Love, love is larger, upright, and virtual. Okay, larger, upright, and virtual. So whenever our object, object location, and every time our object is beyond the center of curvature, then the image properties it'll have will be Sir, smaller, inverted, and real. Okay, anytime it's between center of curvature and our focal point, it's going to be Lur, larger, inverted, and real. And anytime it's between the focal point and the mirror, it's Love, larger, upright, and virtual. Okay? Alright, let's take a look at your diverging mirror. Do you guys remember converging lenses? You remember how all converging lenses have the same properties? It's the exact same thing with mirrors. So we're going to go parallel, but what you have to remember, ding, 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 is that the focal point is on this side of the mirror. Cannot forget that, and has a negative value. Focal point's on this side of the mirror, so you pretend like these don't even exist over here. So it's going to be parallel to focus, parallel to focus. Okay, and then this is a little bit tricky. You're going to go focus to parallel. To go focus to parallel, what you have to do is you're going to put your ruler, you're going to line it up with the focus over here, but the second you hit that mirror, you're going to go parallel, like that. See? So this was parallel to focus. This one is, like, pretend like you're going to the focus, focus to parallel. So you can see this little tiny image is going to be SUV, smaller, upright, and virtual. Remember, this is the real side for mirrors. This is the virtual side. Smaller, upright, and virtual. Okay? So guys, you're going to do the same thing for the rest of them. You're going to go parallel to focus. Whoops, sorry, bit a little bit. Pretend like you're going to the focus, but the second you hit that mirror, you go parallel. Okay, so my pen's bleeding a little bit, but you guys get the idea. Parallel to focus, focus to parallel. Okay, same thing with these guys on the back. Okay, parallel to focus. I need a ruler. Focus to parallel, parallel to focus, focus to parallel. You guys get the idea. Okay, so just remember that this is for concave mirrors. Suv is all for convex. So all object locations. This is like a magnifying mirror, concave mirror. Convex mirror is going to be like the mirrors on that you see like in, you know, grocery stores or, you know, gas stations that keep you from stealing stuff. Those are convex mirrors. All right.